Hello, this is Tom Mack, Technical Support Specialist for Bacharach. Today I'm going to talk about troubleshooting flow faults in a multi-zone fixed gas monitor. Troubleshooting these faults is a straightforward process if you're methodical in your approach and you understand the product. Generally, a flow fault is a result of one or more issues: a system blockage, a mechanical problem, an electrical problem, or incorrect configuration. In this video, I'll explain how to recognize two types of flow faults, what steps you can take to pinpoint the problem, and how to return your system to normal operation. Large volumes of refrigerant can quickly displace the breathable air in a confined space and create a suffocation risk. Be sure to approach all alarms and faults with caution. The severity of these problems may be an unknown, so be sure to exercise appropriate caution when investigating faults and alarms, especially when entering a confined area that may be contaminated with large volumes of refrigerant. The multi-zone gas monitor alerts you if a fault exists. The yellow system fault light is one indicator. Other alert devices may include optional horns, strobes, and even integrated building management systems. In the case of a no-flow zone fault, the word no flow will appear next to each affected zone on the front panel display. The display will also show a fault code that indicates one or more no-flow zone faults. The fault code is a 4-position hexadecimal number that reflects the sum of all current fault codes. So a fault code of 0800 indicates one or more no-flow zone faults. A fault code greater than that indicates the presence of a no-flow zone fault and other active faults. For example, a fault code of 1800 indicates an 0800 fault and a 1000 fault. The 1000 fault is a no-flow on purge fault, indicating a blockage detected in the purge line. That's the line used to draw clean, fresh air into the system. No-flow zone and purge line faults are some of the most common faults that users may experience. They may appear individually or together. I'll show you how to troubleshoot both, but your MZ may only have one or the other. So your multi-zone gas monitor shows that you have one or more no-flow zone faults. This means the MZ is unable to draw a gas sample from those zones, which means those zones are not being monitored for gas leaks. Your next step is to diagnose the cause of the no-flow condition, so it can be corrected and proper monitoring can be restored. The following sections will step you through the diagnosis processes from simple to more complex. The multi-zone gas monitor takes up to 16 zone samples in a continuous round-robin fashion. Using the onboard pump, the MZ draws in a gas sample from the next sequential zone into the infrared bench, analyzes the sample, reports results, and then moves to the next zone. Depending on the sample line length, the number of zones, and how often you configure the system to re-zero, a complete cycle of all zones may take several minutes. So if you make changes to your MZ system in order to address a fault condition, give the system a few minutes to cycle through all zones before re-evaluating the current fault status. The previous fault will remain on the screen until the system cycles through all zones again and no fault conditions exist. The offending zone is resampled, the original fault condition is remedied, and the fault itself is cleared. So your first and easiest action in troubleshooting flow faults is to simply wait a few extra minutes to see if the fault condition clears, especially if you've recently made changes to your system. If the fault persists, you can then continue your investigation. Next are what I call phantom manifolds. This situation may not be the most common, but it is certainly easy to check. Depending on your application, MZs can be purchased with 1, 2, 3, or 4 manifolds, providing either 4, 8, 12, or 16 total zones to be monitored. If your MZ has fewer than 4 manifolds, the unused manifolds are disabled by default from the factory. However, if someone mistakenly enables those manifolds without an actual manifold being present, the MZ will report the corresponding zones as having no flow faults, a phantom manifold. Though this situation is highly unlikely, it is worth a quick check before tackling more complex troubleshooting steps. To check for a phantom manifold, use the Num Zones Installed setting in the System Setup menu to configure how many zones are installed in the MZ. Gas manifolds for the MZ are available in groups of 4 inlet ports each, so this setting can be 4, 8, 12, or 16, indicating 1, 2, 3, or 4 manifolds respectively. Compare the Num Zones Installed setting to the actual number of installed zones, 4, 8, 12, or 16. To do this visually, inspect the side of the MZ chassis and multiply the number of manifolds by 4. This number should match the number in the Num Zones Installed setting. If not, change it. Note that the number of installed zones may be more than the actual number of zones you plan to monitor. For example, an application requiring 10 zones to be monitored will require 3 manifolds or 12 installed zones. In other words, set the Num Zones Installed setting to the physical number of manifold zone inlets installed in your MZ, either 4, 8, 12, or 16. After making the change, be sure to wait for the MZ to cycle through all active zones again and verify that the no-flow zone faults have been cleared. If they have cleared, you had a phantom manifold, but you're all set now. If not, you need to continue your investigation. The next easiest flow fault to diagnose is to confirm that the pump is operating properly. A malfunctioning pump may create reduced or even no vacuum, which may result in a no-flow fault. Here's how to check if your pump is operating properly. From the diagnostic screen, check pressure, ambient, and vacuum readings. Properly operating pumps will show a pressure reading of approximately 1 psi below ambient, or about 13, and a vacuum reading approximately 3 psi below ambient, or about 11. If your system exhibits similar values, your pump is working properly and is not the cause of your no-flow fault. So you need to troubleshoot further for clogs, restrictions, electrical problems, or mechanical problems. If your pressure and vacuum values are not at the typical and optimal readings of 13 and 11, your pump is suspect, but you still need to confirm. At this point, the no-flow condition is likely either a faulty pump or possibly a clogged hydrophobic filter. Isolate the pump by removing the hydrophobic filter from the equation to confirm that the pump is the cause of the no-flow faults. To isolate the pump, do a pinch test of the sample line near the hydrophobic filter. While pinching the sample line, check the pressure value. It should be about 3 psi less than ambient. If so, your pump is fine, so you need to troubleshoot further for clogs, restrictions, electrical or mechanical problems causing your no-flow fault. If not, you have one more test to confirm a faulty pump. At this point, a pump problem is likely to be the cause, but you want to check the exhaust line of your MZ first, just to be absolutely certain. A clogged exhaust line can exhibit many of the same characteristics as a bad pump, so disconnect the exhaust port to see if that clears the faults. If so, troubleshoot your exhaust line for blockages to address the no-flow fault. If not, you want to replace the pump on your MZ. At this point in your troubleshooting efforts, the pump appears to be working properly, so you need to continue your investigation further to determine the nature of the no-flow zone faults. A large differential between pressure and ambient indicates a large negative pressure buildup and is typically seen in the following scenarios: a clogged filter, a line restriction in the sample tubing, faulty solenoid or manifold hardware, typically a solenoid is stuck in the closed position, or a bad solenoid control board. Sample pressure readings would be an ambient pressure of 14 psi and a system pressure of 11 psi. In cases of large differentials like this, it is often fairly easy to diagnose a clogged filter or restricted line, so you should troubleshoot those options first. The opposite of a large pressure differential is a very small or no differential, which can also be the cause of a no-flow zone fault. In this case, there's a very small difference between ambient and pressure, less than 1 psi for example. In this case, an ambient reading might be 14.5 and a pressure reading might be 14.1. This differential of 0.4 psi is very small and is typically seen in the following scenarios: a bad solenoid control board, energizing more than one solenoid, or faulty solenoid manifold hardware, one or more solenoids mechanically stuck open. Let's investigate each of the previous 4 troubleshooting scenarios individually. If the diagnostics value indicate a restricted flow, temporarily remove the hydrophobic filter from the system and replace it with a piece of zone sample tubing. At this point, you may want to try to blow through the hydrophobic filter you removed to verify that it is indeed blocked. After making the temporary change, wait for the MZ to cycle through all active zones again and verify that the no-flow faults have been cleared. If the fault clears, replace the hydrophobic filter with a new one. If you do not have a new filter, either shut down the system or put the old filter back in. Do not operate the MZ without the filter in place. The filter prevents moisture from entering the infrared bench assembly. Replacement of a compromised infrared bench is much more expensive than a replacement of a filter. If the filter removal did not clear the no-flow faults, you need to continue your investigation. If the diagnostic values indicate a restricted flow, there may be a clog in the sample tubing or a clog in the end-of-line filter. To diagnose these issues, locate the connector of the suspect zone on the side of the MZ chassis. Disconnect the zone tubing by pushing in on the connector while simultaneously pulling out on the tubing, effectively eliminating that whole zone. Next, wait for the MZ to cycle through all active zones again and verify that the no-flow zone faults have been cleared for this zone. This confirms either a clogged or pinched sample tube or a clogged end-of-line filter. You'll need to locate and correct the problem. For an end-of-line filter or water stop issue, remove the suspect filter, wait for the MZ to cycle through all active zones again, and verify that the no-flow faults have been cleared for this zone. Troubleshooting the clogged or pinched sample tube may be a little more involved. This may be as simple as locating then removing a kink or replacing a small section of sample tubing, or as complex as running all new sample tubing if the obstruction cannot be found or cleared. If removing the suspect zone sample tubing did not diagnose the problem, the no-flow zone fault is likely being caused by either a mechanical issue related to the solenoids in the manifold assembly or an electrical issue related to the printed circuit board that drives these solenoids. In each of these cases, you will need to continue your investigation to diagnose further. At this stage of troubleshooting, a no-flow zone fault is likely to be caused by either a mechanical problem with one or more solenoids in the manifold or an electrical problem with the printed circuit board that controls the solenoids. To determine which, we'll first confirm that the suspect solenoid in the manifold is actually energizing. You see, if we can isolate a suspect zone and then somehow verify that the solenoid is indeed being energized, then we can assume that the solenoid control board is doing its job and the problem is a mechanical solenoid issue within the manifold. To do this, we must first put the suspect zone into a zone hold state. Next, you can use a magnetic field detector held above the suspect solenoid to verify that the solenoid control board is telling the solenoid to energize. If the magnetic field detector lights, you know that the solenoid circuit board is functioning and the problem is a mechanical issue with the manifold assembly. It will likely need to be replaced. If the magnetic field detector does not light, you can assume that the problem is likely electrical and associated with the solenoid printed circuit board. In this case, you may also have a mechanical problem with the manifold, but really have no easy way to test that in the field if the solenoid PCB is compromised. Not everyone has a magnetic field detector handy, so here's an easy way to check for an energized solenoid on a multi-zone. Lightly hold a small screwdriver or paperclip above the suspect solenoid and move it back and forth very lightly. If the solenoid is being properly energized by the solenoid PCB, you should feel a slight resistance as you move the screwdriver or paperclip back and forth through the magnetic field. If no such resistance is noted, it indicates that the PCB is not properly commanding the solenoid to turn on and the PCB may be compromised. In this case, you should consider replacing the printed circuit board that controls the solenoid. If you do notice resistance, it indicates that the PCB is sending the proper commands, but the solenoid is apparently not mechanically activating. In this case, you should consider replacing the suspect manifold. As a final check to distinguish between mechanical problem, a bad solenoid, and manifold, and electrical problem, a bad solenoid control board, do the following. Power down the multi-zone system. This step is critical, otherwise you'll destroy the solenoid control board. With the power off, disconnect the 4 solenoid connectors. Restore power to the system. Wait for the MZ to power up and complete its warm-up cycle. Check the ambient pressure, the internal pressure, and the vacuum pressure readings. If the pressure, vacuum, and ambient values are really low, approximately 3 psi lower than their original values, for example, 10, 9, and 11, respectively, then a printed circuit board that controls the solenoids is likely to be bad and should be replaced. If the pressure, vacuum, and ambient values are the same as their original values, then 1 or more solenoids are likely to be stuck in the open position. You can confirm this by feeling for air leaks along the external sample line connectors. You can use a flow gauge if you have one, or just move your finger along the connectors and feel for an airflow. It may be difficult to feel airflow from stuck solenoid directly against the quick release zone connectors, so try adding a small length of sample tubing and checking the flow from the end of the sample tubing. It actually makes it easier to detect these types of leaks. So if solenoids are stuck open, you may want to consider removing this and disassembling the suspect manifold to clean the solenoids. Sometimes moisture, condensate, and bits of sample tubing from careless tubing deployment make their way into the solenoid and prevent smooth operation. A careful disassembly and thorough cleaning is usually sufficient to restore proper operation. If you're not comfortable disassembling the manifold to investigate the solenoids, you can always just replace the manifold, though careful disassembly and cleaning is quicker and less expensive. Prior to replacement of an entire manifold, consider swapping a free zone for the zone with the stuck solenoid. Assuming an extra zone is available, just be sure to reconfigure the zones appropriately. Note that this option can only be successful if the bad manifold port is stuck closed. For a bad manifold with a port that is stuck open, the entire manifold will need to be replaced. In addition to no-flow zone faults, your multi-zone gas monitor may detect a no-flow purge fault. This fault shows up as a 1000 fault code and is very similar to diagnosing a line restriction flow fault. You see, the purge line of the MZ is used to supply fresh, clean air for the purpose of purging the system. Don't confuse the term purge with exhaust. The purge line draws in clean air. The exhaust line expels used and possibly contaminated sample air. So let's look at ways to troubleshoot a no-flow purge fault. So if your MZ shows a no-flow purge fault, you may have a clogged purge line or a clogged end-of-line filter on your purge line. To diagnose these issues, locate the connector on the purge line on the side of the MZ chassis. Disconnect the purge tubing by pushing in on the connector while simultaneously pulling out on the tubing, effectively eliminating that whole zone. Next, wait for the MZ to cycle through all active zones and purge. Then verify that the no-flow purge fault has been cleared. If the no-flow purge fault clears, you have confirmed either a clogged or pinched purge tubing or a clogged end-of-line filter. You'll need to locate and correct the problem. For an end-of-line filter issue, remove the suspect filter, wait for the MZ to cycle through all active zones again, and verify that the no-flow purge fault has been cleared. Troubleshooting the clogged or pinched purge tube may be a little more involved. This may be as simple as locating, then removing a kink or replacing a small section of tubing, or as complex as running all new purge tubing. If removing the purge tubing did not diagnose the problem, the no-flow purge fault is likely being caused by either a mechanical issue related to the solenoids in the manifold assembly or an electrical issue related to the printed circuit board that drives the solenoids. In each of these cases, you will need to continue your investigation to diagnose those components. Although a blockage in the purge line and a clogged end-of-line filter are the most common causes of a no-flow purge fault, there may be a sample tubing length issue. Note that the length of the purge line plus the length of the exhaust line must not exceed 1,200 feet total. If they do, your multi-zone gas monitor may be exhibiting signs of a no-flow purge fault. Diagnose this by carefully verifying the sum of both distances and reducing those distances if needed. Well, there you have it, a summary of how to diagnose and troubleshoot most no-flow zone and no-flow purge faults on the multi-zone gas monitor. By having a few tools on hand, performing regular maintenance, and following proper installation and configuration practices, you can all but eliminate these types of faults, providing years of trouble-free gas monitoring. The multi-zone is American-made and quality tested for years of service. If a mechanical component eventually does reach its end of life, it's a straightforward process to locate the issue and replace the component quickly and easily. For additional support, you can simply call your local Bacharach support line. Knowledgeable technical support personnel will guide you through the process of troubleshooting and diagnosing any issues you may have. Global sales channels, quality products, long life, and support if you need it from our corporate offices in the US, Ireland, and Canada. A few more reasons why Bacharach is the measurable difference.